So now let's go to checking model assumptions now. So we're just going to be looking at our models now. Look at the residuals. We're going to run the residuals. Residuals are actually the difference between our predicted and actual values. Then we run the fitted values, then we run the standardized results. So these are standardized residuals. So I'm just going to standardize residuals here. So these are, you can see these are standardized residuals. So first of all, we want to check for the assumption of linearity. So we are looking for a random scatter around 0, a red line. So this is actually supposed to go, is going to draw 4 plots for us on one graphic window. So 2 rows, 2 columns. Why this particular one plots calculates the margin around the plots. So this is what we're interested in. You can see our fitted values and these are residuals, which are already gotten from this place. So you can see them. So I'm just going to plot using just the base R plot function. I'm going to plot it. So let me run it. So you can see what we're having. So you can see our plot. You can see the way it's looking like. So linearity, and you can see what they explain it. We're trying to look for random scatter around 0, red line. So you can see the red line. So we already put our AB line, which is our red line. You can see we already put our AB line, and we expect this particular green line that we drew, we expect it to be close to the red line. But if you see a curved pattern or systematic trends, if you see something curved, this one is also a little bit straight. If you look at it, it's a little bit straight. So you can see it's a little bit straight. But if you see something curved that is not almost linear, then that means that your data has violated the assumption. So this is also another partial residual plots for continuous predictors. Let's look at another partial residual plots. You can see it, residuals versus the age. And let's look at models with 2 also. Let's look at both of them actually. So this is residuals versus fitted values. This is the residuals versus the age. This is also the residuals versus the models weight. You can see it. So this is models weight with the age, and this is also with the fitted values. I can see all of them are showing the signs of linearity. So for the test of independence, we are going to be plotting the residuals in order of data collection. Let me call this. So if you look at this now, plot residuals in the order of data collection. So we're trying to look for random pattern, no trends or cycles. So you can see this is somewhat like a random pattern too also. There is no trend or cycle, even though we can see we have some of them scattered in this place, but it's not forming a particular shape like a trend or maybe a cycle. Then we now can see that these particular observations are independent of each other. So our graph is showing somehow of a random pattern. If you look at it, it's neither trending or is even having a circle shape whereby it's going up or coming down. Then we can see this particular data has already satisfied the assumption of independence. Then we have the normality check too also. I'm just going to clear this plot. Then let's look at the normality check. So we have the QQ plots. We already have our residuals, so we're going to be checking the QQ plots. Let's see. So you can see the QQ plot is almost on a straight line. So this means that what this observation is normally distributed. So you're going to put your residuals and just put all your details here. You can use the same details for your data too also. 19. Then we have the QQ line, which we also put in this place. This one is going to plot it, while this QQ line is going to bring out that particular red line. You can also use the histogram too also. Just clear this. So this is the histogram which I'm going to be running. So you can see the histogram is forming a normally distributed shape. Now, if you look at this particular histogram now, you can see it's normally distributed. So you can see that what is showing a bell-shaped curve. We can see that this particular data is normally distributed. So we have the Shapiro-Wilk test now. So the Shapiro-Wilk test, if you look at it now, we have a p-value of 0.7919, and our null hypothesis is that the data comes from a normal distribution, while the alternative hypothesis is that the data does not come from a normal distribution. So since our p-value now is greater than 0.05, it means we are not rejecting our null hypothesis, and this indicates that our data comes from a normal distribution, which also corresponds with the image we just got currently. So now we have the homoscedasticity check now. So just going to clear this plot and run the homoscedasticity check. So you can see I told you that what they have to be almost equal, the up and the down. I explained this in the presentation. So they have to be almost equal, which means that what our data is almost scalar-static. We also have the scale location plot too, also that our data has to be showing almost equal patterns both at the up and the bottom of this particular line. This is standardized residuals. We use the fitted residuals and the residuals in the first plot, scale location plot, using the standardized residuals, which is the square root of the absolute of the standardized residuals in the scale location plots. So that's how we're able to get these particular two plots. So these plot functions are just simple. You just put your fitted and your residuals, and the rest are just plot settings, as you can see them here. Your PCH is just more or less size of the points and things like that. So you can look at the plot function to learn more how it works. So just make sure this is the default scatter plot function in base R. This is the plot function belongs to this particular place, so just click on it here. So you look at the plot function, you are going to be looking at the default scatter plot function. So this is one you are going to be targeting. You click on it, and so these are the various arguments which you can use to create various plots to check for your assumptions. So this is base R plot function. We also have what we call the Bruch-Pagan test for heteroscedasticity. It's also another test which you can use in conjunction with your graphical visualization of heteroscedasticity. The null hypothesis is that there is no presence of heteroscedasticity, while the alternative hypothesis is that there is presence of heteroscedasticity. So now let's look at our data. Now this is our full model. You can see it. We're going to be running the Bruch-Pagan test on it. So from our Bruch-Pagan test, our value is 0.1596, which means we're not going to reject the null hypothesis, which means that what there is no presence of heteroscedasticity inside our data. So you can see that already satisfied that particular assumption. So these are comprehensive. Another comprehensive diagnostic test we can also run. You can see we use the plot function. The plot function, if you use it on the whole model, if you use it on your model object, this particular plot function is going to give you comprehensive diagnostic test. So you don't need to be running all those previous plots we have been running. So let's view it now and see. So you can see we have residuals versus fitted. This is going to check for linearity. We have QQ residuals to check for normality. We have scale location to check for almost scalar-staticity. And we also have residuals versus leverage. So this is a comprehensive diagnostic test, so that you are allowed to check for the linearity, independence of observations, normality, and also what heteroscedasticity.